Yeah, I'm going to use this simple example to explain the logic behind the process of hypothesis testing. Suppose I claim my coin is fair. My coin is fair means the head side and the tail side are equal weighted. So each side has the 50% to appear when you flip it, right? When you toss it. And to test my claim, you are going to do a few trials. Yeah, of course, the number of trials, the bigger the number of trials, the better. Yeah. So you are going to do many trials. You're gonna throw or toss my coin many times. Let's say you have a lot of time. You toss it 1,000 times. 1,000 is a very good, very large number. Yeah. So here you would have a sample. Each trial give you a result, right? Yeah, you record the result. The first time I get the tail, the second time I get the head, the third time I get the head, blah, and so on and so on. So you actually, the 100 trials give you a sample with the sample size 1,000. Suppose among the 1,000 trials, 905 of them, 905 times of the 1,000 times are head. Okay, yeah. Here I should point it out. What is X represent? Yeah, X represent the number of times the head shows up. The head shows up. Okay, and then you would conclude, because for a fair coin, this high percentage of head among 1,000 times. Yeah, so if we do the frequency, sample frequency, sample proportion, yeah, we use p hat to represent sample proportion. It is the quotient of x and n. So I have a 905 over 1,000, and that is 9.05%. My bad. That is 90.5%. So if the coin is fair, we should have about 50% to get the head, around 50% to get the tail, right? But now the result shows the frequency, the proportion of heads among the 1,000 trials is so high, 90.5%. Yeah, that can be seen as a rare event for a fair coin. So we say the rare event right now occurs, right? Yeah, we have a rare event rule. What is the rare event rule? Rare event rule says in one experiment, we assume the rare event will not occur. Suppose the rare event occurs and something must be wrong. Yeah, that means the assumption is wrong. So here the rare event occurs because the percentage is so high, and your process of toss the coin 1,000 times, you didn't cheat, right? Yeah, you just normally toss the coin 1,000 times. The process has nothing wrong with the process. The rare event must be caused by the claim. So your conclusion is my claim is false. I claim my coin is fair, but turns out the head side appears with a very high frequency. That then you would conclude my claim is false. Yeah, that means my coin is probably not fair. Yeah, since the head side had such a high frequency, it probably the tail side is very heavy, is heavier. So that's why the tail side always on the floor, and you see the head side. Does that make sense? Does that make sense? So the hypothesis testing is based on the rare event rule. If the rare event occurs in your experiment, one experiment, when the process has nothing wrong with it, and your assumption, you can see this as assumption, your assumption must be false. Yeah, let me know, am I clear about the logic behind the hypothesis testing? Yeah, your process is to test my claim. Yeah, hypothesis testing is to test what? Test a certain claim. It could be any claim, but in statistics, we are going to test the claims about population proportion, population mean, population standard deviation, right? That kind of thing. Yeah. So let me know, am I clear about the logic behind it? Okay, yeah, very good. So next up, we are going to go through some components. Yeah, important components in the process of hypothesis testing. In this section, we do not actually test the parameter, a claim regarding a parameter of the population. In next section, section 8.2, 8.3, 8.4, and we do that. But this section, as the basics of hypothesis testing, will only focus on understanding those pieces, those components closely related to the process of hypothesis testing. All right. So the first thing I wanna say is the process of hypothesis testing, starting from identifying the original claim. OC. Sometimes I write OC, and you want to know that means that refers to original claim. Okay. In our book, in this class, because our class is a statistics, the original claim is a claim regarding either population proportion or population mean or population standard deviation. Yeah, so that's the original claim. And based on the original claim, yeah, so first we need to identify the original claim and write the original claim as, you know, in an algebraic expression. Yeah, for example, your original claim is P, your population proportion bigger than 70%, or your mu is equal to 20, or your standard deviation is less than or equal to 10, something like that. Yeah. So use the inequality or equation to represent your original claim. After the original claim, you are going to give your null. This is called a null hypothesis. Yeah, H sub 0 represents the null hypothesis. If I pronounce that wrong, please let me know. No, right? Not no. Yeah. Sometimes I say zero hypothesis just to make my job.
I think it's pronounced null hypothesis.
Was I saying the same thing?
I think so. Null hypothesis is good.
Thank you. Yeah, no. Some specific thing is hard for me. Like say down. I never be able to say it. So null hypothesis. Okay. So H sub 0, H is the initial of hypothesis. And with the subscript 0, H sub 0 represents null hypothesis. Always, okay? Always. And besides null hypothesis, we have H sub 1. Sometimes you see H sub A, but our book uses H sub 1. And what is the H sub 1? H sub 1 is the alternative hypothesis. Yeah, that's why some book use H sub A, because A is the initial of alternative, right? But we use H sub 1. H sub 1 is better, yeah. So based on your original claim, you are going to come up with or construct or create your null and alternative hypothesis. The idea is your null and alternative has to be has to claim different thing, okay? Has to claim different thing. So in order to reinforce this part, original claim, H sub 0, H sub 1, let's look at examples. Let's look at number 12 here. Let's start from number 12. There were a few questions about that. Here. Number 12, claim a minority of adults would erase all their personal information online if they could. All right, the first sentence is the claim. Do you think we can identify our original claim from that? Do you think we can identify our original claim from the first sentence? A minority of adults would erase all their personal info online if they could. I would, for sure. Yeah, the big company use your information to make money. Okay, so how do we identify the original claim? As I mentioned that our claim, yes, awesome, thank you, Kelly. Our claim is either about population proportion or about the population mean or about the population standard deviation, right? Yeah, so with that known, so this is going to be easier to identify. This actually is about the population proportion or percentage, right? How do we understand minority? Majority means more than half. Minority would be less than half. So our original claim can be written as P is less than 50%. Okay, yeah, depends on the question. Yeah, our question says type an integer or decimal. So you don't want to enter 50% because 50% is not decimal. So you want to enter P is less than 0.5. You don't want to enter 1 or 2. Even is correct. Yeah. So you want to enter P is less than 0.5. So that is our OC, okay, original claim. Yeah, so far so good? Yeah, that's the original claim. Our process starts from identifying original claim and write the original claim in an algebraic way. Yeah, like this one, we use an inequality to describe the original claim. Okay. Once we have the original claim, we are able to construct the null and the alternative. Very, very important thing is the null. Something wrong with my board is jumping. The null always can turn equal sign. Okay? Yeah, that's something we need to remember. It's a convention. Yeah, that's the way it is. Yeah, there's no y. Of course, there's a y behind it, but mainly we want to just accept it and follow it. So remember the null hypothesis. The null hypothesis always can turn equal sign. Yeah, they already give you equal sign for this question. So our null in this case would be population proportion equal to 0.5. And our alternative would be the same with the original claim. Yeah, another thing I want you to write down and remember is one of the two hypotheses, H sub 0 and H sub 1. One of them, and only one of them, has to be the same with the original claim. Since the null has to contain equal sign, in our case, H sub 0 not possible to be the same with the original claim, right? Then H sub 1 has to be the same with original claim. So that's how do we figure out H sub 1 is the same with original claim and it is P less than half. All right, am I clear about that? Two things, okay? Two things. Your null, any null hypothesis, any null hypothesis has to contain equal. Yeah, either P equal a value or mu equals a value or sigma equals a value. All right, that's about the thing that we need to know. Yeah, the null hypothesis always have to contain equal sign in it. That's the first thing. Second thing, h sub 1 and h sub 0, one of them and only one of them has to be the same with the OC, original claim. Okay? Yeah, since our original claim is p less than 0.5, it's not going to be the null. It has to be the alternative. So that's how do we know our alternative is p less than 0.5 and our h sub 0 is p equals 0.5. Does that make sense, guys? Yeah. Why is that? Why do we make the null has full? Yeah, because the null represents our sample or a certain treatment, because you are trying to claim something, your sample, right? So equal basically means there's nothing, doesn't make any difference. It does not make any difference. The sample result does not make any difference. But the original claim means from the sample, it does make a difference. It's less than half, less than half. So let's see. Do you understand what I'm talking about right now here? Two things about that part. Okay, yeah, very good. Number 13. I should have covered the answers, should I? Yeah, but I didn't have time to do that. So you see the answer already, but you don't have to see it. You can just you can cover it, use your hand, right? Okay, number 13. Claim the mean pulse rate, yeah, whatever the unit is, yeah, beats per minute, yeah, of adult males is equal to 68.9. Oh, okay. So this original claim is about population mean. Yeah, we clearly see the keyword mean here. So population mean is that notation mu. Yeah, equal is equal to, of course, is equal to 68.9. So 68.9 beeps per minute is your claim. Yeah, you claim the mean pulse rate for male is that many times, right? Every minute. Yeah, that's our original claim. So based on the original claim, we want to find h sub 0 and h sub 1. Remember, h sub 0 has to be always a contain equal sign. In this case, since our original claim contain equal sign, we have h sub 0 same with original claim. Yeah, again, h sub 0 has always contained equal sign. Then what about h sub 1? Because if you read through the question, it does not say, yeah, for a random sample of 170 adult beats, the mean pulse rate is 68.5 BPM, and the standard deviation is that. Complete the part A through part B. Yeah, we are going to only do the, so you know what, those are unrelated. For this type of question, we don't really need that. Okay? We don't really need those information. All we need to know is the first sentence. All we need to know is the original claim. And how do we know the alternative is not equal to? Why the alternative is not bigger than or less than? Why is it not equal to? Yeah, when it does not specifically point it out, the complement of equal or the opposite of equal would be not equal. So that's how do we know h sub 1 alternative is mu not equal to 68.9. Not only because the question already tell us. Yeah, if it doesn't tell us, we should still know, okay? Yeah, we should still know. Any question about number 13? Also, two things. The null hypothesis has to contain equal sign. That's the first thing. Yeah, I know I repeat that already. Second thing is one of the h sub 0 and h sub 1 has to be the same with the original claim. So since h sub 0 has to contain equal sign, so in this case, the original claim and null is the same. All right, and then the alternative is the other side of the claim of the hypothesis, the opposite. Any question about number 13? All right, thank you. Then let's continue number 14. Claim. The standard deviation of pulse rate of adult male is more than 10. Okay, so this claim, original claim, is about the standard deviation, population standard deviation sigma. And is more than 10. That's the claim, right? So the original claim is sigma is bigger than 10. Sigma is bigger than 10. So that is the original claim. And based on original claim, we are going to come up with the h sub 0 and h sub 1. Remember, h sub 0 has to be always equal to, right? Yeah, always equal to, and whatever the claim, the standard deviation, gonna be used in h sub 0 and h sub 1. Okay. Yeah, has nothing to do with in this step. Identify OC, h sub 0, h sub 1 has nothing to do with your sample yet. You do not have a sample yet. You do not have a sample yet. You only have a claim that you are going to test. So the h sub 0 is sigma equals 10. 10 is your claimed standard deviation, population standard deviation. And h sub 1 would be, remember, OC has to be either equal to h sub 0 or equal to h sub 1, right? Yeah, that's how do we know? Since in this case, OC is not going to be the same, with h sub 0. The OC has to be the same with h sub 1. So h sub 1 is a sigma bigger than 10. And that's how do we get it, all right? Yeah, make sure that even you don't have those things, you still be able to figure it out. Because when you actually test a claim, they won't give you these things. They won't give you that. You have to come up with those three things. Original claim, h sub 0, h sub 1. Again, h sub 0 always contain equal sign, and original claim is either equals h sub 0 or equal to h sub 1. Yeah, one of them has to be the same with OC, original claim. Any questions? No? Okay. Okay, thank you. Yeah. So number 15, those questions are very similar. Claim most, yeah, when you see most, majority, yeah, you're gonna guess probably is about percent. Yeah. Most adults would not erase all their personal information online if they could. Would not. Oh, this is not about that. Okay, let's see, what is this? Okay, that's not about the claim. So yeah, those questions, number 12, number 13, number is about the first step, we can say that, the process. Identify original claim and h sub 0 and h sub 1. Okay. Go back to the no part. A lot of small things here. Yeah. So once you identify your original claim, h sub 0, h sub 1, you want to decide your alpha. What is alpha? Alpha is your significance level. I mentioned this before in chapter 7. This alpha is the same with the confidence level alpha here. Yeah, if you are confident with 1 minus alpha, then the part you are not confident would be alpha. All right, that alpha actually represents the probability of a mistake, a type of mistake. So alpha here, the name of alpha is called a significance level. Significance level describes the seriousness of making type 1 mistake or type 1 error. Yeah, about what is type 1 error? Type 1 error is your original claim is your null is right, is true, but you wrongly or incorrectly reject it. Yeah, that is a type of mistake when you do the test, hypothesis testing. Yeah, your H sub 0 is true, in fact is true, but you conclude is false, so you reject it. That's a mistake. And alpha here measures the seriousness of making that type of mistake. So of course you wanna lower the seriousness of the mistake, right? So alpha is gonna be a very small number. Common use the alpha value include 5%, 0.05, or 10%, or 1%. Yeah, 5% is the most common used significance level. It survives from the past. In the past, when technology wasn't this advanced, calculation is easier when you have a convenient significance level like 5%. And even now, when our technology can do any type of number, 5% survives and thrives actually, or you can say it stuck. The tradition remains. Yeah, we keep using 5%. And there are statisticians, they argue that 5% is too high in certain situations. So really, when you do your research, really depends on your the feature of your research. If the feature of your research is about like medical, like about people's life and death, you want to make alpha as little as possible. So 5% might be too big for you. So you would have to adjust that. Yeah, but for us, we still use 5% because it's convenient, right? If we couldn't use 5%, we would not use 5.1% or 4.9%. Okay, so alpha is called a significance level. It measures the seriousness of a type 1 error. And type 1 error is you mistakenly, you wrongly reject the null when null is true. All right, so that is alpha. We want it as small as possible. And what does alpha here, what's the usefulness of alpha? We use alpha no matter the method we use, okay? We mainly gonna introduce two different methods. The first method is called a p-value method. The second method is called critical region method. Our book introduced the third method called confidence interval method. I'm not going to include it here because I do not think it's a good idea to use confidence interval to test, because confidence interval is to estimate. Also, confidence interval method is not equivalent to those two methods. Those two methods are equivalent because in a sense that they always have the same conclusion. Okay, they always have the same conclusion. So we use alpha for both methods. All right. At this point, all we need to know is alpha is called significance level. Yeah, it's actually the same alpha in confidence level 1 minus alpha, and it measures the seriousness of making a certain mistake. So we want it as low as possible. Yeah, so we want it as low as possible. Yeah, we have a formal definition for significance level. We can read it together. The significance level alpha for a hypothesis test is the probability value used as the cutoff for determining when the sample evidence constitutes significant evidence against the null. By its nature, the significance level alpha is the probability of mistakenly rejecting the null when it's true. All right, it's a good paragraph to read. I don't think it's super easy to understand. I just describe that as alpha is represent the seriousness of making the type 1 error. All right. Any question about alpha here? No? Okay. So since we mentioned type 1 error and type 2 error, yeah, we are going to talk about that in this case. Yeah, because alpha is the probability of making the type 1 error, right? So we're gonna talk about type 1 error and type 2 error here. Type 1 error refers to the mistake that you reject H sub 0 when it is actually true. All right, alpha is used to represent the probability of type 1 error. And what is type 2 error? Type 2 error is, so this is always about a null, okay? Yeah, it's always about null. Like your sample doesn't make a difference. So beta, we use beta to represent type 2 error. Actually, to represent the probability or measure the seriousness of type 2 error. What is type 2 error? Type 2 error is you accept, no, you fail to reject. So it's different, okay? Fail to reject. Fail to reject doesn't mean you accept, by the way. You fail to reject just means your sample fails to reject. You can do another sample, right? Some other people can do the same thing. Doesn't mean you have decided to support the claim, the null. So type 2 error is the mistake of fail to reject the null when the null actually is false. Yeah, I think the two type of errors is very easy to understand. Type 1 error is you reject when it's all about a null. You reject it when it's true. And type 2 error is you fail to reject it when it's false. All right, and we have a power of hypothesis test here, a new concept. The power of a hypothesis test is 1 minus beta. We know 1 minus alpha is confidence level. Then what is 1 minus beta? 1 minus beta is called the power of a hypothesis test. Is the probability 1 minus beta of rejecting a false null hypothesis? The value of the power is computed by using a particular significance level alpha and a particular value of the population parameter that is an alternative to the value assumed true in the null hypothesis. Alpha is more important. We don't have many things about the beta. I think for us, all we need to know is the definition of beta and the definition of a power of a hypothesis test. We have a question about that. Hold on, this is number 7 and behind after. So look at the homework questions. We can go through the first few. Number 1, a hypothesis test is a procedure or process for testing a claim about population parameter. Number 2, the null is a statement that the value of a proportion parameter is equal to some claimed value. So null always has equal sign in it. Number 3, we don't do number 3 yet. Number 4. This is about tails. Numbers, okay, we can do tails here, yeah. Which of the following is not true about the tails in a distribution? So once we have the original claim, h sub 0 and h sub 1, we would be able to determine the tail. So we have 3 types of tail: right tail, left tail, and two-tailed test. Yeah. So this actually question this is about what type of test we are going to deal with, to apply to test the claim. So if you see this, and that is the right tail, doesn't matter there, okay? Yeah, because OC has to be the same with H0, one of the H0 and H1. So if you see this notation, inequality symbol, you have a right tail. If you see this notation, you have a left tail test. If you see this notation, you have a two-tailed test. Yeah, that's about it. So number 5, which one is not correct about which type of tests we are going to apply? We have 3 options: right tail test, left tail test, and two-tail test. Part A says the tails in a distribution are the extreme critical region bounded by critical value. That's correct. B, so we just look at this one. How about that? The inequality symbol in the alternative hypothesis points away from the critical region. Yeah. So since the h sub 0 always contain equal sign, then our alternative has 3 types: either this or this or this, right? Yeah. When it's bigger than, strictly bigger than, that is right tail test. When it's strictly less than, that's left tail test. When it's not equal sign, not equal to, is a two-tailed test. So it says the inequality symbol in the alternative hypothesis points away from the critical region. It's actually point toward, right? You want to know the correct way, the right statement about this part. The inequality symbol should point toward the critical region, not against. If it's against, then it's gonna be left tail, point against. So this is point right here. Okay, it's supposed to point it toward. Yeah, this means right tail. This is left tail. This is two-tailed. For number 7 is about the 2 types of errors. Let's see number 7. Which of the following is not a true statement about error in hypothesis testing? Choose the correct answer, but we are going to choose the one which is incorrect, right? Which is false. A, error is the mistake that rejects h sub 0 when h sub 0 is true. This is a true statement. B, a type 1 error is the mistake rejecting null when it is false. So this, of course, is false, right? C, the symbol alpha represents the probability of type 1 error. That's correct. D, type 2 error is making the mistake of failing to reject null when it is actually false. True as well. Are we good with number 7? Are you guys still with me? Yeah, this section it's not very easy to organize because it's just a few pieces, many pieces related to the hypothesis testing. I thought about doing 8.2, 8.3 before 8.1. But I did not do that because I think we should we should get familiar with those concepts first. So that's number 7. Number 8. Number 8 is about the power of hypothesis test, right? Yeah, 1 minus beta. Yeah, that's all we need to know. 1 minus beta is called the power of hypothesis test. Yeah, it's the probability of rejecting false null hypothesis. So beta is a mistake. Then 1 minus beta is not a mistake, right? Yeah, it's the chance you actually correctly reject a false null. So that's called the power of hypothesis test. And this question is about, let's see. Okay. Let's do number 10. Identify type 1 error and the type 2 error that corresponds to the given hypothesis. The percentage of households with more than one pet is less than 65%. So when you see percentage, and you know that's about the population proportion. The notation for population proportion is P. So the given hypothesis. So this hypothesis can be represented by P is less than 65%. Okay. Identify the type 1 error and the type 2 error that correspond to the given hypothesis. It did not point out that this is this is one hypothesis. You know what? This must be H sub 1. This must be H sub 1 because it does not have equal sign. And your H sub 0 would be the one with equal sign, right? P is equal to 65%. Identify type 1 error. Choose the correct answer below. A. Type 1 error, let's recall, is the mistake that you reject the null when it's actually true. Okay, so we assume this is true, but you mistakenly reject it. Yeah. So let's read the ABCD. A says fail to reject. When I see that, I'm going to move forward. Yeah. Do not fail to reject null. It's a reject null when it's true. When it comes to type 1 error. Part B, reject null. Yeah. Now that the percentage is less than, okay, that doesn't make sense because that's H sub 1, not null. Okay, so that's the reason we do not choose this one. And C, reject null. And what is null? The null is that the percentage is equal to, yeah, that is correct. Yeah, the null has to contain equal sign when the percentage is actually equal to, yeah. So part C is the correct answer because it correctly states the null. Yeah, the null has to contain equal sign, and also correctly states the null hypothesis. When it's true, also correctly states the type 1 error. When the null is true and you reject the true null. And part D, fail to reject. When I see that, I know it's not gonna be false, right? Yeah. Any question about number 10? About type 1 error. Are you guys still with me? Okay, very good. Thank you for your response. Okay, very good. Number 11. Oh, okay, we are not done yet. Number 10. Number 10 has another part. Identify type 2 error. This type 1 error, this type 2 error. Choose the correct answer below. Let's recall what is type 2 error. Type 2 error is when a null is a false. We fail to reject it. We fail to reject it. So let's read a ABCD. Again, we have the null, which is P equals 65%. Part A, fail to reject. Yeah, that probably something we should keep reading. Fail to reject the null. What's the null? The percent is less than. Okay, that's why it's wrong. We don't do that. We don't choose A. A is wrong because it has a wrong description of H sub 0. H sub 0 has to be equal, not less than. Part B, reject null, so that doesn't work for type 2 error. C, reject null, that does not work for type 2 error either. D, fail to reject null. And what's the null? The percent is equal to 65%. So D is correct. All right, D is correct. And this is a good question. Help us to understand the two types of errors and also reinforce one thing that I repeatedly emphasized earlier. The null has to contain equal sign. The null has to contain equal sign. Okay. Number 11 is also about type 1, type 2. Number 11, identify the type 1 and the type 2 error that correspond to the given hypothesis. It doesn't say what's the hypothesis, but we can figure it out. Percentage, so P, is bigger than 88%. This must be H1 because H0 has to contain equal sign, right? The percentage of adults who have a job, is greater than 88%. Okay, so the null would be the percentage equal to 88%. Again, null has to contain equal sign. Let's read the answer choices and select the one correctly describe the type 1 error. Type 1 error is to reject null when it's true. So we are not going to choose this one, not going to choose this one. We look at A and B. Reject null, and what's the null? The null states the percentage of adults who have a job is equal to. Yeah, that's the reason A is correct. Yeah, what happened to B? B says the null is the percent is greater than 88%. That's incorrect. That's type 1 error. Type 2 error, these two questions are very similar. Type 2 error is fail to reject the null when the null is false. So fail to reject. I would not choose this one. I would not choose this one. I would choose fail to reject, right? And which one would be the correct one? And let's see how do they describe the null hypothesis. So this one, null hypothesis is greater than, hold on, percentage who have a job is equal to, oh, okay. Yeah, that's correct. Equal to 88%. And that's enough for us to make a decision. That statement is correct, is true. And this one says the percentage, the null statement, null hypothesis is a percentage is greater than. That's not correct. Right? So that's about the two types of errors. Two types of errors. So the two types of errors related to alpha, and alpha significance level is something you predetermined before you test the hypothesis, the claim. And next, I'm going to talk about test statistic. As you can see, we have 4 rows in this problem, right? And how do we understand test statistic? Test statistic is something come from a sample. First, we need to know that. That follow a certain distribution, like we are able to handle. Yes, so far, what distributions we have learned? We have learned a normal distribution, especially standard normal, right? We have to learn the t distribution. And we have not learned this yet. It's called a chi-square distribution. We'll see later. So test statistic based on the parameter of the population you want to claim about. You take a sample and use the test statistic, come up with a test or expression. Yeah, come up with an expression that can be represented by a variable, and that variable follow a distribution that you know or very familiar with. For example, z distribution or t distribution. So we're going to talk about that later in later sections. Yeah. At this point, we need to know what we need to know is the test statistic depends on the parameter we want to claim for and the sample. And the sample is come from a sample. And next, we are going to talk about p-value. P-value is very important, but also controversial. Some people claim that p-value method is not really good method. But we're going to learn that method as one of the 2 methods for hypothesis tests. In a hypothesis test, the p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample. Yeah, I don't really like the definition a lot. Assume the null hypothesis is true. So p-value, what we need to know about the p-value is p-value is a conditional probability. Conditional probability. It refers to the probability that suppose the null is true. Suppose the value is true, null is true, and you get a result or rare event. Your result is even rare, how do I say that? Rare than alpha. Your result is suppose h sub 0 is true. and your result is even less likely than the criteria. Alpha here is the criteria. We always compare p-value with alpha. Remember, alpha measures the seriousness of type 1 error. Yeah, suppose h sub 0 is true and you reject it. That's a mistake, right? And we want this as low as possible. And the p-value actually is the probability that your result is even less likely than that. Your result is at least as extreme as the test statistic obtained from the sample data. Result is rare or the same rare than, I would fix this, sorry, test statistic. So let me explain how does the p-value methods work, all right? Suppose our test is a z-test, and we use a z-distribution, just for example. And remember, we have 3 types. One type is left tail. The other type is right tail. The other type is 2 tails. And p-value actually is the, let's say, suppose this is our test statistic. For left tail test, our test statistic must fall on the left side, left tail. For the right tail test, our test statistic fall in the right tail. For two-tailed tests, and you would have 2 of them. You would have 2 test statistics. One is positive, the other is negative, and they both are the cutoff, separating the significance high and significantly low, and with the region that is not significant. And the p-value actually is the area of that. P-value actually is the area of this for the left tail test, and this for the right tail test. For the 2-tail test, we are going to use twice of the one side of the area. Yeah. So I have here to explain what I'm trying to say earlier. If it's a 2-tail test, then p-value is twice of the area in the tail beyond the test statistic. I don't know if you know what I'm talking about here. In general,
I mean, I guess the question that pops into my mind is, isn't that area infinite? So it just sort of seems odd.
The area is not infinite. Yeah, that's a very good question. Remember, the area between x-axis and the curve is 100%. 1 is a finite number, right? 1 is a finite number. Yeah, my drawing is not the best. Yeah, my drawing isn't the best. Yeah, they're supposed to be like the curve supposed to have the horizontal scale as the asymptote. So even you see is open, it's always open here, right? But actually the area is a finite number because the area between the curve and the x-axis is 100%. Remember that? That's the one of the important property about the density curve. Always equal to 100%. Yeah. So of course, this area, this tiny area, is just a part of one, right? Just a part of one. Of course, the number is going to be a finite number. Yeah, I apologize. My drawing isn't the best. My drawing should with the tail very small. Yeah, but if it's very small, it's really hard for me to show you. So I draw a very fat tail. But the tail is supposed to be very tiny, very skinny. Did I answer your question?
That did, and it's not so much the drawing. I thought it was just part that they never touched the x-axis, so that it was infinite. But yes,
yeah, it never touched.
You're right. Curve is one, so yeah.
Yeah, you are right. Never touch. If you go to higher level math, you learn the sum of infinitely many numbers. Yeah, sum like series. Yeah, sum of infinitely many like terms or items, right? Yeah. So there's two types of this thing. Yeah, one is a diverge, one is a converge, and this happen to be converge. So it exists and it is a finite number in this case. It's an assumption for the curve to be a density curve. The assumption is the area between the curve and the x-axis must be 100%. Value 1 is finite. So part of it is also finite. So let's see if we have some also, okay. So how do we use p-value to decide, are we going to reject the null or not reject the null? So here there's a very catchy thing. I don't know you guys, how do you call this thing, this type of thing that could help you to remember. If p is low, if p-value is low, null must go. Null must go. If p-value is high, null must fly. Well, now you're gonna wonder, low, how low is low? So low or high is compared with alpha. Your predetermined significance level. If your p-value is lower than alpha, then null must go, means you're going to reject null. If your p-value is higher than alpha, null must fly, right? Means it survives. So you fail to reject null. You fail to reject null. So that's something we can remember about the p-value, or how do we use p-value to make the decision about the rejecting null or fail to rejecting null. All right, so so this table, I'd like you to take a screenshot of this table. Our book gave you a flow chart. I really don't like the flow chart, so I typed this table for you. Is more convenient to apply, more convenient to use. So once we decide reject null or fail to reject null, we need to have a formal conclusion. Yeah. How do we make the formal conclusion? You follow this table, okay? Yeah, we're gonna talk about this table later, in later chapter, in later section, when we actually need to make the conclusion. That's the last step. Yeah, let's go over more questions on the worksheet. Number 3, the what is a value used in making a decision about a null and is found by converting the sample statistic to a score with the assumption that the null is true. Test statistic, okay? Yeah, it's different from p-value. Remember, p-value is a probability. Yeah, the main difference between p-value, And the test statistic is p-value is a probability. Remember, it's a probability, so it can be represented by area, right? A certain area of the region under the density curve. But test statistic is a value, okay? Yeah. So if we need to really calculate it manually, p-value, we have to either use normal CDF or TCDF. And if we need to find the test statistic, depends on distribution, we have to use inverse normal or inverse T. Am I clear about that? Yeah, that's something I want to point out. If you tend to confuse one with the other, actually they are so different. They are so different, right? So based on the description of number 3, the answer is supposed to be test statistic because the value, the value used in making a decision about rejecting null or fail to reject null, and is found by come up with an expression using the sample statistics, and and make sure the expression can be represented by a variable, and a variable has a certain common used distribution. Yeah. So here it says different thing, seems different wording from what I said, but in essence the same thing. Used in making a decision, and is found by converting the sample statistic to a score with the assumption that a score, what's a score? Z-score or T-score, right? That Z-score has a standard normal distribution. And that's why Z-score is important, because we know its distribution is a standard normal. Or T-score. Why T-score, not other score? T-score follows T distribution, and we know T distribution, right? Yeah, so you have to make sure the expression the test statistic is a common used score, either Z-score or T-score, that we know its distribution. Yeah, that's number 3. Number 4, which of the following is not true about the p-value? A, if p is low, no must go. Okay, that's correct. I just told you, right? Lower than alpha. B, p-value is an area. That's correct. Didn't I just say that? P-value is an area, right? Yeah, it's a probability. So it's area. And C, if p-value is high, no must fly. I also mentioned that earlier. Yes, it's true. If it's higher than alpha. D, p-value separates. No. P-value is not score, so it does not separate. This is supposed to be changed to critical value. Critical value separate the critical region. All right, so D is false. Any questions so far?
And just to clarify, critical value is a test statistic?
No.
Okay.
No. Yeah, that's a very good question, Kelly. Critical value refers to Z sub alpha, something like that. For 2 tails, Z sub alpha over 2 plus or minus. Critical value only depends on alpha. Test statistic depends on other statistics from the sample. You know what I'm saying? Like the table shows.
Yes, okay. That makes sense. I just was like, well, we're talking about values and test statistics, so is critical value a test statistic? But okay, sounds good.
Yeah, test statistic is different from critical value. Yeah, that's a very good question. Test statistic depends on many other things. Actually, it doesn't depend on alpha at all. Yeah. Test statistic depends on sample only. Only depends on sample. Critical value only depends on alpha. Yeah, that's a very good question. Critical value versus test statistic. Critical value only depends on alpha, and it will give you the critical region. Yeah, we're going to talk about critical region method in next week, so you would know what is critical value. But test statistic only depends on sample. Yeah, you convert a sample to a certain score whose distribution is well known. Z-score, T-score, Z-score, again, chi-score. Yeah, so this is good to take notes for. We run out of time. I think you probably can do the rest on your own. Concepts. All right. While we still don't know the methods, the two methods, clearly know what's the two methods to test the hypothesis, to test the claim, and we are going to get that answered in the next week when we actually test a claim regarding p or mu or sigma. The class will be more organized, and I'll show you how do we use technology and or manually to get that done. All right, guys, if you have any questions, you're welcome to email me. I'll say good night now. Let me take a picture of the attendance. Oh, that's sad. We lose some students, don't we? I remember we have 10 participants. Oh, we have 10 participants. Now we only have 8. Yeah, don't rush to leave before I say I take a picture of the attendance. Okay, guys, have a good night, everybody.